and he'll talk about randomized asynchronous iterative linear solvers.
Thank you, Ali, and thank you for inviting me to come and give a talk here. So I'm going to talk about asynchronous linear solvers for symmetric positive definite matrices. And I want to start with some motivation why we are looking on asynchronous methods. So I'm going to give two motivations. One is more related to applications in big data. And I'm going to ask you a question. So we want to solve AX equals B. A is symmetric positive definite. It's large, it's sparse, and we want to use an iterative method because the matrix is too big to do a direct method and it has structure that is not very good for direct methods. And the question, should we use Gauss-Seidel or CG? I mean, Gauss-Seidel is a very old technique. It was invented based on relaxation on fixed point iterations. It was invented before CG. And usually it's not much used today because if you look at the theory, you know that CG will converge in square root of the condition number. There's also dependence on the epsilon, which is log 1 over epsilon, which I'm kind of ignoring now. But Gauss-Seidel, if you take a randomized version of it, not the classical one, which I'll give details on the randomized in a few slides. If you do the convergence, it's only the amount of iterations is proportional to the condition number. So if the condition number is big, this can be a big difference. So why would you want to use a Gauss-Seidel? Well, you then try it on a matrix. For example, because this big data I took a matrix from big data, and this is a matrix from doing some regression on social media data. And in general, the results do match the theory. You really see that CG is progressing much faster. I didn't continue beyond 200 iterations, but it's clear the trend. I mean, if you continue to the right, I mean, CG will bypass the randomized Gauss-Seidel here, which is stuck. I mean, it's on slightly below 10 to the power minus 3. It will continue to go to very high accuracies. But what is interesting is that if you look at the start, you tend to see the Gauss-Seidel-based method, this very cheap, small iteration method, they tend to make a lot of progress early on. And what happens is that in many applications, specifically for the application we were looking on here, this is all the accuracy you need. If you go beyond that, you're not getting anything in terms of the downstream use for how this solution is used. So if you do just 10 iterations, take this solution, you get in all you can hope to get from solving this equation. But if you do 10 iterations of CG, you're up here, and you lose a lot in terms of the iteration. So you need to continue up to here. And if you continue here, of course, you're not getting anything. So you really want to be around here and to take this method that it does a lot of fast initial progress. But of course, as Sivan mentioned, to have good software, you need to parallelize that. And there's quite a few ways to parallelize it. We looked at an asynchronous way to parallelize it, which is, I think, quite easy, an easy way to do it, and we can show that it gets you good results. So I'm going to give you a second motivation, and this is more like a well-known trend. It's not a concrete example of an application. Is that CPU clock speeds have reached the limit, and we have to use more processors. But as we get to really large processor counts, we know that there's a problem with communication and between those processors, and specifically there is a problem with scalability because of synchronization points. That if you have P processor, you do need to do order of log of P just to synchronize them. So if P is very large, then you're paying a lot for the synchronization points. And because of this trend, asynchronous methods are becoming more and more attractive. You do want to avoid the synchronization points as you go to higher processor counts. So asynchronous numerical methods are pretty old. They're probably the oldest. Well, the idea is basically, I must say that, is to avoid the idle time, but just letting processor progress without explicitly synchronizing between them, just using maybe information that is a bit old. And the idea was perhaps first suggested in '69 with chaotic relaxation, and since then it's been applied to to a lot of applications, but they were never really considered mainstream and not very popular compared to methods like CG or things that are synchronous. And there might be there's a few reasons for that, and I'm going to give you my take on it. The issue is that the analysis is usually based on fixed point iterations, so you can only prove convergence in the limit, and that's a little problematic because you don't know how it behaves in practice. And really, there's examples of of matrices where the asynchronous method converge very slowly. So we don't understand about them. The concurrency is usually not enough to see any benefit, but they are much slower than the synchronous counterpart, so it's not very attractive. And finally, that's even more severe restriction problem, is that the traditional method often places very severe restrictions on the matrices they can prove convergence. For example, diagonal dominance, like Sivan discussed in the previous slide, is one of those conditions where it was known that various asynchronous methods converge. But more general, like take symmetric positive definite matrices without any structure, then there were not known algorithms for that. But now there's more recent work, and I'm going to give detail a few that are relevant. There's some work in a distributed setting on agents. That's not like the talk yesterday. That's not the setting we are talking about. It's a different setting. We are looking at a shared memory or distributed memory setting. But from that line of work, there's one method that is more related to what we are presenting, and it's on synchronizing clocks. It's based on the Karpman's method, the same method Sivan discussed in the previous slide, and that's some similarity to the method we are going to describe because we are using Gauss-Seidel, which is related to the Karpman's. Much more relevant for this talk is the recent work on Ogwild, which is basically an asynchronous parallelization of stochastic gradient descent. There's a convergence rate analysis. You can say how the asynchronous affects for a shared memory model. And our analysis is inspired by this, but it's significantly different, and we have much better convergence for this specific problem of solving linear equation. So I'm going to give details on an asynchronous solver for general symmetric positive definite matrices. We can show it converges in a provable rate, and its condition number, it's linear, and it's a randomized algorithm, so all error bounds are going to be an expectation. So I will start with some background on randomized Gauss-Seidel, what that means, and then give the algorithm and some experiments. So let's start with randomized Gauss-Seidel, and I will explain that using some basically a very simple iteration, an almost obvious one, especially after the first talk today, which is basically doing coordinate descent, maybe doing coordinate descent on this function. But let's start with a more general setting where we have A and X, and we have some direction vectors D. And we always want to do steps in those direction vectors, which I'm not specifying them yet. So we do this kind of equation, where here we have some step size gamma sub j. And we have this formula. Why is this? Where comes this formula? Well, this is the formula that will minimize the error in the A norm of the next step. This is an analytic equation. If you just do that, that's the minimization of this one. So it really makes sense if you are greedy to do these steps, if you select a direction, just to use these gammas. But the question is, of course, how to select these direction vectors. And actually, most methods to do iterative solve linear equations can be cast as this kind of iteration. Even CG just as a clever way of selecting these direction vectors. And one simple way to select them is to just do a round robin on the coordinates. Just look at the identity vectors, where you just take the first identity vector, the second identity vector, so forth, and cycle. And this, if you kind of look at the equation long enough and try to figure out, you'll see that this is equivalent for any iteration of the classical algorithm of Gauss-Seidel. It's a different way to describe Gauss-Seidel, but it is an equivalent one. And what's nice about these direction vectors is that the iterations are very small and cheap. You need only one entry of the residual of this guy, of the difference between B and A times X. So you need only one row to look at one row of the matrix to compute this guy, and then you can do this step very efficiently. Okay, so how this works? Well, to analyze it, you can analyze using classical techniques in fixed iterations, but if you want, a new somewhat more attractive way that relates things to a condition number is to look at a randomized version of it, where you select the direction vectors, not in a cyclic way. You kind of select them with some probability. The probability should be proportional to the diagonal values. And then if you use this kind of way to select the direction vectors, you can bound the expected A norm of the error after m steps using basically reducing by some factor that is smaller than 1, so you have a linear convergence. But what really governs the convergence is this ratio of the smallest eigenvalue and the trace of the matrix, which is the sum of the eigenvalues. So the running time is going to be proportional to the inverse of this guy, which is the trace divided by the smallest eigenvalues. And since the trace is bounded by n times the largest eigenvalue, number of iterations is bounded by n times the condition number, but n iterations is about equivalent to one matrix vector multiplication, so this is like equivalent to basically order of the condition number of doing as much operation in CG here, which basically the matrix vector is the most expensive operation. So this is the way to analyze. This is the analysis, and I'm going to go quickly through the analysis because it's going to be useful later on when we analyze the asynchronous method. It's a very simple analysis. It can be put in one slide, but there's a few more details maybe, but basically this is all the analysis. Basically now, we are going to assume that from now on that A has a unit diagonal. We can always achieve that by rescanning the matrix. And then basically we want to look at the step size, which is basically this expression with equal probabilities. And then you can just do very simple algebraic manipulation so that the A norm after J plus 1 iteration is related to the A norm after J iteration minus some term that is positive. So it's positive, that's what we progress. But again, now this is a random variable, so we can if we fix the residual, it's basically the average entry in the residual. But this guy we can always bound using the eigenvalues like this, and then take expectation of both sides, and then we get the bounds on the expectation on how much we progress, and we take the lower bound and plug it in here and just get the bound we described. And I'm here also giving an upper bound. We can bound how fast we can progress. This is, of course, not something you usually want to do, but when you're going to analyze the asynchronous method, this is going to be important, actually. OK, so now we are going to get to the asynchronous version. So before that, I'm going to give some pseudocode of the synchronous method. So this is just a pseudocode. Basically, at each iteration, you select a random entry. You read the entries of x that you need to compute the step size. You compute it, and then you just do the update. And now I'm going to describe the asynchronous version. It's a very small, very easy variant of this. Basically, I'm just taking this algorithm, and I'm executing on all processors. And all processors are going to share the vector x. But all of them are going to not share anything else except have the same shared x in shared memory that they are going to operate. So this is the algorithm. I said all our processors execute the same algorithm. And I'm going to do two small modifications of the algorithm. First of all, I'm going to require the updates here to be atomic. So you can do that usually using hardware, but it means that nothing can interfere in the middle when you're doing these operations. And I'm also going to add a small step size here, beta, which has to be smaller than 1 to show convergence. But it can actually be quite close to 1. So this is the two small modifications. And now we want to analyze this. So to do that, we need to write the iteration in some meaningful way. So the writes are atomic. So we can order the updates in some order, some serialization of the updates. And we can write some fictitious iteration x sub j, which is basically all the updates that happened up until the j, after j iterations, basically some linearization. And now what happens in the asynchronous method is that when you're reading the entries here on the line 4, some of the updates that happened before that are going to be read. You're reading the vectors, you're going to see updated values, and some are not. Some may be updated, you read them before they were updated or something like that. So you can always describe a set of k of j of updates that are consistent with the vector you read. The vector you read must be, because the operations are atomic, must be consistent with some set of updates. So you can have some maximum set. And then you can always describe your iteration in terms of this additional kind of non-existing iterations that are dependent on set of updates. You can describe x after a specific set of updates as occurred, as basically just taking these updates. And you can describe your iteration as in terms of the residual on that iteration that actually never happened, but you can describe your iteration in terms of it. So you can write some useful expression for how xj plus 1 looks as a function of x. This doesn't work anymore. xj, OK. Now you want to analyze this. And of course, you have to make some assumption, because if you allow some updates to never be read, you will have arbitrary slow convergence. So you need to assume there is some bounded asynchronism, which we say, we have a parameter tau that really says that all updates that are older than tau will be read when you get, will be read at a specific iteration, which is, this is just a formal way to say that. Every iteration that is old enough will be read. And of course, you need another assumption, is that you're not really completely adversarial, because if you kind of set the KJs when you know the random choices here, then that can really mess up your convergence, but it's not a realistic assumption. So we allow KJs to be arbitrary, but they cannot depend on the actual random choices. Okay, so now I'm going to be slightly more technical in the analysis in a few slides. I apologize for that. So we can do the analysis starts by just doing some algebraic manipulation to write the error after j plus 1 iterations as a function of what happens after j iterations, plus some progress here that is always positive, and then some additional terms that isn't always positive. That's something that really comes from the asynchronicity. It measures the vector that we would have wanted to see and the vector that we actually see. So we have some progress that is positive, but this can be negative. But the idea is that since these two guys are different by only tau coordinates, and matrix A is also sparse, so this guy can be, in many cases, will be 0, because the entries that are non-zero here might not be the entries that are non-zero in that specific row, because we are selecting a specific row. So with that probability, this guy is going to be 0. With other probabilities, it's going to be actually bad for us. It's going to slow us down. But the idea is to try to bound this negative effect. So now you, of course, take expectation, and you have this you have reduction in the expectation, and some term that now is positive because we take an upper bound. And this guy depends on basically on this thing that is a measure of basically how sparse the matrix is relative to the size, because we have 1 over n here, but this guy is always smaller than n. But if the matrix is sparse, this guy is going to be 1 over n, so we have a very small component here. Another nice thing is that the progress is proportional to beta, but the damage here is proportional to beta squared, so we can always set beta to be small enough that this guy will be bigger than this guy. And the final observation that is really useful is that the guys that appear here in the expectation are basically guys that appeared in previous iterations. Because this one can be bigger than this one, but it's always much smaller because of these coefficients than the progress we made at previous iterations. So we kind of need to basically do kind of compensation with the progress made in some iteration by the damage that is caused in this iteration. The way you can do that is basically now take a sum, just aggregate, write the error after k iterations as a function of the first iteration and all the progresses that were made, and then we can bound the progress by some lower bound and get this expression on the expected error of after m iteration. So this is still a little difficult to analyze because we have here only upper bounds on this guy, so we cannot really show enough progress. But the way you need to do this is, again, like I said, you need the upper bound. You need to show there's enough progress because you only have upper bound. You need to show that the progress is not too fast. So because what happens is that since your progressor is proportional to the error after in the previous iterations, if these guys are too small, then you are not showing any progress. So you need to bound these guys from below. That comes from the slide before earlier on that I showed some lower bounds on some upper bounds on the rate of the progress. So you use this guy, and you can show that after you did enough iteration, which is proportional to the number to n, then you have some reduction in the expected error by some constant factor that depends on the condition number. And some constant here that really captures what the asynchronism does. So hopefully, if row 2 is small, then this guy is going to be small. So if we do enough tiny steps, then the expected error goes down, decreases by some constant factor, and then we can occasionally synchronize the thread in order to reduce the expected error. But of course, we don't always really want to synchronize. This is like we synchronize every n iteration, which is not that bad. We don't need to synchronize every iteration, but we are still going to synchronize about the same amount of time as we are going to do like CG. So we can work a little harder, and I'm not going to give the details, and you can show a bound without any additional synchronization. The terms are much more complicated. So this is the results, and it appears in the paper. And Now, we cannot do additional assumption if you really want to improve. So here you have a dependence on tau squared, which is basically the square of the number of processors. And here you have enough tau cubed. You can improve this if you kind of enforce somehow that you read entries that are always consistent, that the interests that you read are consistent with some iteration. Then you can show an improved bound which depends only on tau. So you are linear in the number of processors, and then you basically have a weak scaling regime. But of course, enforcing this can be a little hard. It might be maybe some hardware that allows you to do that, maybe transaction memory, but it's still not easy to enforce this. But this analysis is not completely useless in the sense that because the matrix is very sparse, usually the entries that you read will be consistent with some iteration. So the real behavior, if you don't do anything, the real behavior will not be this, but it will not be this as well. So it will be something between the two. But in terms of the bound, you have to make this assumption if you want to show a stronger bound. Sorry. So now some experiments. This is, again, the same matrix before, arising from social media analysis. And we use a single blue gene Q node that has 16 cores. Each one of them can do 4-way upper threading. So there's total of maximum amount of 64 threads that we can spawn here. And now we take this matrix and we run it. And again, the y-axis is the running time. And so lower is better. And it's a logarithmic scale, and also the number of processors is a logarithmic scale. So we see that the asynchronous method, as we expect, because everybody is independent, really has linear speed up. And it continues to around 48 times faster at 64 threads. And consider that some of these threads are virtual. I mean, we only have 16 actual cores, so this is pretty good speed up. CG is actually parallelizing pretty well as well, but as the number of processor gets up, you kind of see that it deviates from the linear speed up, and if you add more threads, then it will probably tends to flat out. And at 64 thread, the asynchronous method is twice faster. And here I'm doing 10 iterations because that's all we need for the application. And so are you paying that in terms of the residual for using an asynchronous method? Well, you are paying something. The theory shows that, but you're not paying a lot. So the black line is what happens if you just use randomized Gauss-Seidel on this matrix. No asynchronicity. You do a synchronous method. It's 48 times slower, but it gives you slightly better results after 10 iterations. It gives you around 10 to the power minus 3. And the asynchronous method is slightly higher, but it's still the same order of magnitude. It's not a big difference that will really affect how you're going to use the solution. So conclusion, we have a new approach for asynchronous linear solvers. It uses randomization to gracefully handle the non-deterministic asynchronous behavior. Now, if you look through the slides, we never made some assumption on the symmetric positive definite matrix. We only assume that it is sparse enough so that there's not too much collisions when you're doing the asynchronous iteration, but we are not imposing any structure or limitation on it. So we don't need something like diagonal. We can apply it to a wide range of matrices, and I just took one application here that usually, if you use traditional method, they cannot even show convergence for it. And for most matrices, okay, this is maybe a slightly strong claim, but for many matrices, it will converge if the matrices are relatively sparse. It's linear convergence in terms of the condition number. There's some slowdown due to the asynchronicity, but it's not too big. And for least square, you can probably generalize this to the randomized Kalkmars and get similar convergence rate. And Sivan discussed that tiny steps are bad for parallelization, but asynchronicity can maybe handle that. So that's some of the idea of using asynchronicity to use these tiny steps, but in parallel, basically. And that's all. On the randomized Kalkmars, or so you're talking about something else?
Asynchronous.
Coordinated. So I saw he gave some talk about that, but I never saw a paper. So I don't know the details. I met him in February, and he mentioned that he's working on that.
The paper is very freshly out.
Is it out? Is it on archive or something?
Yeah, I think so.
Okay, so I'll look for it.
So our example matrix, I think it is 1,000 non-zeros per row.
It is, yeah, something like that.
So did you choose it on purpose?
No, this is a real application.
Denser side, I think, and then you said sparser is better for your method.
So no, that matrix, I wanted a matrix that I wanted a matrix that it makes sense to do these weak iterations that really get the benefit. And I had some guy who did this analysis on social media. I cannot say exactly what the analysis is, but this is the matrix he had, and I said, this is the matrix that is good for this method, and it turned out to be good for this method. So.